So, Kevin, we are going to talk about the way that some compounds form, in fact, maybe all compounds form, and some handy rules that we have for keeping track of the ways that compounds form and that I think are reasonably readily understandable. Okay?
Okay.
So I want to go back for a second, back to the photoelectron spectroscopy. We saw when we were plotting this photoelectron spectroscopy data that in this lower set of orbitals, in the 1s orbitals, we can have a total of 2 electrons. And we saw that in the second level, the 2s and the 2p, you can have a total of 8 electrons. And then we continued on into the third and the fourth level, showing 8 electrons and 2 electrons. We got that from the photoelectron spectroscopy data that we built based on the experiments. Fair enough?
Yep.
Okay. And then we take those and we can take that same information. In fact, if I take, we've seen energy level diagrams, like here's one for hydrogen, which shows 1 electron in the 1s down here and no electrons in the 2s and the 2p, right? So we've had these energy level diagrams, different ways of trying to understand what's going on the atomic level. Okay?
Okay.
And if I plunk down helium on top of it, here's helium with its 2s electrons. And nothing in the, sorry, with its, yes, it's 2 electrons in the 1s and nothing in the 2s and nothing in the 2p. So that's helium. We jump ahead a little bit to oxygen. Oxygen has 8 electrons, 2 electrons in the 1s, 2 in the 2s, and 4 in the 2p. And we know that as a neutral atom, oxygen has that particular configuration. And the next element over, fluorine, has 9 electrons, 2, 2, and 5 up here in the 2p. So we know those things already, and it feeds directly from the photoelectron spectroscopy data. And it says that for some of these elements, having 2 electrons down here in this lower 1s orbital is really important, really stable. Having 8 electrons in this second level are really important, really stable, and so on as we go up and across the periodic table. So we've seen in some compounds like H2, it forms by this 1 hydrogen electron and another hydrogen electron in an adjacent atom coming together, and these 2 electrons being shared by these 2 hydrogens. We've written hydrogen this way often, right, to show two dots, 2 electrons being shared by those 2 hydrogen atoms. And that's how we understand the bonding formed in hydrogen. How am I doing?
So far, so good.
Okay. All right. So now, and we also know that if we look at oxygen, we have drawn oxygen 1, 2, 3, 4, 5, 6. Oop, I blew it. 6. 6. There we go. 6. That's a really big electron for the oxygen. And I'm going to draw another oxygen because I drew that one like that. 1, 2, 3, 4, 5, 6. And we know that we've often drawn oxygen by sharing these electrons. If I go back to my energy level diagram for oxygen, 1, 2, 3, 4, 5, 6, 7, 8. So here are 2 pairs of electrons, 2 lone pairs of electrons for my oxygen, that one and that one. and we've got these two other electrons hanging around. Well, it's very easy to imagine that if I share these electrons in my oxygen, I've now brought these two electrons in close to these outer orbitals. I'm going to draw it as a dotted line in there for now. And so this oxygen, this original oxygen, and this other oxygen one, two, three, four, five, six. And now this dotted line electron was this one over here, and this dotted line electron was this one in here. And so they merge, as those two oxygen atoms get close to each other, they overlap and share those 4 electrons. You'll see in Cengage a series of animations that show this much more beautifully than I can show on a piece of paper. But what this leads to us to recognize and see time and time again, that with oxygen and with lots of elements in that row of the periodic table, they form by getting 1, 2, 3, 4, 5, 6, 7, 8 electrons in the outer orbitals of this oxygen. 1, 2, 3, 4, 5, 6, 7, 8 electrons in the outer orbitals of this oxygen. And so in the text, in Cengage, you'll often see some reference to something called the octet rule. And that's just a way of saying that when compounds form, many of the elements that we deal with will end up with 8 electrons in their outer energy shell. Just like we saw here, 8 electrons. Now, sometimes those elements get them by gaining electrons. So if we look at oxygen here, oxygen had 2 and 4, and so it tries to share 2 electrons or gain 2 electrons to get to a total of 8. If we look at fluorine, 1, 2, 3, 4, 5, 6, 7, 8, 9, it needs 1 more electron to have its 8 electrons. We look at fluorine here beside oxygen. Make sure I got the column right. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1 more electron, and the fluorine will have its octet of electrons. So the origin of the octet rule is sitting there for us inside the photoelectron spectroscopy data. I want to point out, though, 2 other rules, one of which is used commonly by chemists, but maybe not so much in this course, but in classes that come to the future that we might encounter in the future, and one that nobody ever names, but is actually part of the same deal. I'm going to share my screen and bring up a periodic table here. So we were looking at hydrogen, and it needs 1 more electron to fill its outer orbital. Helium already has 2 electrons, and we've seen that it's non-reactive. It's a stable gas. You buy it in balloons at grocery stores and at party stores and that sort of thing. If we can have an octet rule for this second row of the periodic table and an octet rule for this third row of the periodic table, then I would say we can have a duet rule for hydrogen and helium. So I would say before we even have an octet rule, we have a duet rule. And it applies to hydrogen and helium. First 2 elements of the periodic table, the only 2 elements in the top row of the periodic table. And the reason that is because we've seen hydrogen has 1 electron. It only needs 1 more electron in this orbital, and it is now perfectly stable, perfectly willing to bond and form compounds that way. Over and over and over again, we'll see hydrogen doing that. The duet rule for helium has 2 electrons. It already satisfies the duet rule. It satisfies the duet rule, and so it doesn't react at all, but it obeys this duet rule. So if I go back here, we see hydrogen and helium duet rule. We look at the next row of the periodic table, 1, 2, 3, 4, 5, 6, 7, 8. That gets us to the octet rule. 1, 2, 3, 4, 5, 6, 7, 8. Octet rule. And so these compounds try to form, these elements try to form compounds by satisfying the octet rule and by getting 8 electrons in their outer orbitals. In the second row, the case of the 2s and the 2p. In the third row, the case of the 3s and the 3p. So here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And this is called the 18 electron rule. And it manifests itself in a couple of different places that we see in chemistry, but it's the 18 electron rule. And it works for the exact same reason that the duet rule worked, and it works exactly the same reason that the octet rule works. And it has to do with elements further down the periodic table wanting to fill up the 4s, the 3d, and the 4p across row number 4. And subsequently, the 5s, the 4d, and the 5p. And so the duet rule, the octet rule, and the 18 electron rule all come from the same orbitals being filled as we go across the periodic table. Would you like to ask a question, Kevin?
I don't know if I want to ask this, but on the periodic table, there is another set of elements on the bottom.
Yeah. And I was thinking, it's been a long time since I've counted that across. I think we probably should know the answer to this one, but let's pull it up and let's do it as long as we're on this one. So it must be the, I don't know how many fingers and toes you got, Kevin, but here we go. 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. Did I skip something?
No, okay. I was pretty sure it was 32. I'm glad we double checked.
Yeah, I think it is. And we might be able to figure it out by subtracting 54 from 86 and getting 32 as well, right? That's another way. You are welcome to use the math however you want to. The same rules apply. Number of electrons that are trying to fill available, and number of orbitals that the elements are trying to fill with electrons. Fortunately for you and I, in this course, almost everything we're going to do is in these top 3 or 4 rows of the periodic table. So we really only have to worry about the duet rule, the octet rule, and the 18 electron rule.
Okay, sounds good.
Excellent question.